Okay, today we're going to talk about logarithms, and we're going to start right off with some of the applications of logarithms that are used in present-day situations. For example, I imagine you've heard of loud sounds being measured in decibels. Well, those are measured in a logarithmic scale. And another use of a logarithmic scale is the Richter scale, which hopefully you've heard of in reference to earthquakes. So in the Richter scale, what's incredible there is if you have such large explosions of great magnitude that they are measured where if you have a Richter scale measurement of 6, that is actually 10 times if you had a Richter scale measurement of 5. Okay, so the key to the Richter scale is for every point that it goes up, every unit that it goes up, that's really 10 times the lower measurement. So 5 to 6 is a 10 times expansion of the magnitude of the earthquake. That's why when you get up to like a magnitude of 8, they're talking very, very serious damage caused by earthquakes. So that'll be the first part of your homework, is to look at some Richter scale measurements and say how great the magnitude has increased. Okay, the next thing I think we want to talk about is negative exponents. And I know there were some questions about this from the last time. All right, you never want to leave your final answer with a negative exponent. So what are we talking about, negative exponents? For example, 5 to the negative 2. What is that? It's simply the reciprocal of the base, and then you have the squared. So that's 1 over 5 squared equals 1 over 25. And by the way, you would never leave your final answer as even 5 squared. Your mom doesn't say go out and get 5 squared eggs. She's going to say probably going to get 2 dozen eggs, but 5 squared is 25. So you write it out. This would be the number that this is equal to. So let's take another one. What if we had x to the 7th over x to the negative 2? What would that be? Well, you can take the base with a negative exponent and move it to the other side of the division line, and it becomes a positive exponent sign. So this becomes x squared up here, and you have x squared times x to the 7th, which is x to the 9th. Okay, what about 3 over x to the negative 4? Well, the 3 doesn't move. It's okay. But the x to the negative 4, I have to move that up. So that's 3. And when I move it to the other side of the division line, it changes the sign of the exponent, 3x to the 4th. What about x minus 4 to the minus 4 power over 3? What would that be? Well, got to move this down, and this becomes 1 over 3x to the 4th. Okay? All right, the first thing about logs is let's talk about the definition of the different parts of a log statement. And next time we're going to go over why logs were created. But for right now, let's skip right in to the format. So if I have a log statement and then it's got a base, And then it's got a funny thing called the argument. And then that might equal y or x or whatever. Okay, so let's take an example of this. This would be log base 10 of, let's see, 10. And what would that be? That actually is 1. Okay. Why is that? Because we can convert from the log form to an exponential form. If you remember that logs equal exponents. Very important. Logs equal exponents. So, if a log equals the exponent, then I'm going to write this in exponential form now. This is the base right here. So that's the base of the exponent. The log equals the exponent, so that's 10 to the 1. And that equals what? What does that equal? 10, which is the argument. Okay, this is that 10, and this is that 10. All right, let's do another one that'll make a little more sense, perhaps. Let's evaluate log 1/10. Well, how do we do that? Well, first of all, where's the base? Sometimes we write logarithms and we don't show a base. If you do that, that means it's automatically a base 10. That's called a common logarithm. Common logs are all to the base 10. So you could say that there's a 10 here. And if I'm evaluating this, log of 1/10, I'm going to put that in there just to help me do the conversion when I convert to exponential form. And then I'm going to set this equal to x, because that'll tell me if I can figure out what x is, then I know the value of log 1/10. All right, well, let's convert. What's the base? 10. Logs are exponents, so the exponent of the base is x. And that would be equal to the argument, which is 1/10. Okay, so what does that mean? If 10 to the x equals 1/10, well, remember in our discussion of negative exponents, this is the same as 10 to the negative 1, isn't it? Okay, if that's equal to 10 to the negative 1, and that's 10 to the x, do you see these two things are equal? They're both base 10. They've got to have the same power. So x has to equal negative 1. If x equals negative 1, then log 1/10 equals negative 1. Okay? Let's do another one. Let's say we've got evaluate log of, say, 10,000. Well, okay, the log of 10,000, that's base what? It's a common log, so I'm going to say it's log 10. and I'm going to set it equal to x. All right, now I'm going to convert that into the exponential form. The base is 10. The log equals the exponent, so the exponent of the base 10 is x, and that equals 10,000. That's the argument. Remember, this is log, base, argument equals the exponent. Okay? Well, what would that be? 10 to the what power equals 10,000? So x equals 4. So the answer to this problem is 4. We've evaluated log 10,000. Okay, finally, let's take our parent function chart, domain and range. Take a look at that and fill this in for the logarithm. All right, and what is the rule for the logarithm? That'll just be log x. All right, let's take a couple of points. You can get your calculator. X, y equals log x. See, and if it's 0, what's log of 0? That's undefined in your calculator, isn't it? If it's 1, then that's 0. And if it's 10, that's 1. All right, let's see what this graph's like. So here's my origin. This graph comes up like this. It's 1, 0. And then it goes like this. 10, 1. Wow. All right, let's fill this in. Now, by the way, this continues to go up as it moves to the right, but very slowly. And in other words, it has to go all the way out to 100 before it gets up to 2. So it goes up very slowly, but it does continue to go up. All right, so this has a vertical asymptote of x equals 0. And that's down here. This gets closer and closer to the y-axis as it goes down here. It continues on, it never touches the y-axis. So what's the domain? The domain is x is larger than 0. And you could write that in interval notation as 0, infinity. What about the range? Okay, well, the range, this goes infinitely down from the bottom. So where does this come out? And as I said, it continues to go up. So actually the range is all real numbers, but it takes a long time for it to get very high, doesn't it? What about the y-intercept? There is no y-intercept. Okay, and one last thing that I'd like to talk about in regards to this graph is what would be the inverse. Do you remember inverses? That's when it's a reflection across y equals x. So what would that be? Well, let's take a look at these points. 0, 1, 0, 1, that'd be here. And then 110 would be up here, out here. And then this graph would be like that. And here, it's going to mirror this. So what is the inverse of the log function? This is actually 10 to the x power. It's the exponential function that we talked about last time, 10 to the x. Okay, I think you can do that homework, and we'll continue with our log discussion next time.